Morning, professors and friends. Thank you for coming so early in the morning for my talk. This is a presentation on the Throughput and Ad-Hoc network with wired access points, and my name is Ritabrata Roy. I'm a new PhD candidate at WINLAB. This is the outline of the talk. It's really going to be a short presentation, about 30 minutes or so. It's going to be on introducing the topic, then the analysis that I've performed, and finally the results. So we'll be looking at the problem definition, the motivation for the problem, and discuss some of the previous results which led to this problem. So our aim over here is to obtain the throughput of an ad hoc network which contains n nodes, a fraction q of which have wired connections and can act as access points. So it means that you have an area in which there are n nodes, nq of which, since the fraction q, nq of which have wired, so they can both receive and transmit signals wirelessly, but they also have wired backbone, as a result of which it can communicate with the other access points. And the remaining 1 minus q times n nodes are pure wireless nodes. And we intend to compare the results we obtained from such a setup with the results that were obtained by Gupta and Kumar in their pioneering paper on throughput of wireless networks. And in fact, this problem was partly motivated by the fact that Dr. Kumar came here to the IMAX conference and gave a presentation of his work. And it was immediately followed by this question. Now, we can consider this network with wireless nodes and wired access points as similar to the cellular phone network. For instance, in a cell phone, you would typically, when you're using the cell phone, you would communicate with the base station which is in your cell. And if you're, for instance, making a nationwide long-distance call, the different base stations communicate between each other, typically through wired lines. And again, at the other end, there is a wireless connection. So same thing would be happening over here. A sensor node, which is typically a wireless node, would communicate to its nearest access point, and the access points would then communicate through the wired backbone, and on the other end, the access point would send the signal to another wireless node. So one of the advantages of doing this would be that it would prevent, as we know, when there is a wireless transmission, every other node within that range cannot transmit. So that way we are going to improve the throughput. So the motivation for this problem, because as I mentioned, one of it was followed immediately by, it was Dr. Kumar's talk led us to think about this. And in fact, WINLAB is pursuing a project which is called the Hierarchical Ad Hoc Network, which has a kind of three-tier layer, in which one of the layers is the wireless sensor node, which sends its information to the wireless forwarding node, which finally goes to the access points which are wired. So what we're looking at over here today is somewhat a simplified version of this, which has just two tiers, the access points and the wireless sensor nodes. Moreover, we can also think of the access points in this problem as a kind of gateway, which is connecting to the outside wired world. For instance, if you have an ad hoc network which wants to access the internet, an easy way to do that would be to get in touch with an access point which is wired and hence get connected to the rest of the world. So this is the result that I was referring to earlier, the paper by Gupta and Kumar. They show that the throughput per node is of the order of W by square root of n, where W is the transmission rate of each node over the wireless channel. Now, I'd like to point out an important term over here, which is that the traffic patterns are assumed to be optimally assigned. This seemingly innocent term encompasses a large number of assumptions which might not be very realistic. They include the fact that the location of the nodes are assumed to be known. The traffic pattern is also assumed to be deterministically known. Then there is no collision between the packets. And finally, the nodes are all static. They do not move around. Now, Gupta and Kumar had quite a bit of difficulty in trying to convince the world that these results actually hold good, that with the increase of number of nodes in an area, your throughput actually goes down, because intuitively it's not very obvious. In fact, it might appear that by increasing the range of each wireless node, you might be able to increase the throughput. But that is not true for the simple reason that whenever you increase the range, all other nodes within that range cannot transmit. So because of that constraint, your throughput actually goes down. And since I already used the analogy of the cellular phone network, it's akin to thinking that if you have a cell phone which can actually, instead of communicating with your nearest base station, if it transmits much further, what would eventually happen? What would happen is that the cell size would gradually increase, frequency reuse would diminish, and eventually you'd have fewer number of users. So that's kind of intuitive interpretation of this result. And
I have to admit, I don't like that analogy because in a cell phone setting, that's just a waste of resources. Because the goal is to connect to the base station, right? So why would you transmit, with more power than you need to reach that base station, right? Whereas in their setting, right, the argument's a little more subtle because by transmitting with more power, the message travels further, right? So in essence, like their situation is significantly more subtle than the analogy you're making. So, but, it calls the question here. Anyway, go ahead.
okay, so by increasing the power, the node would actually reduce the number of nodes that could perform or transmit in that region simultaneously. In this paper, the authors show that the aim would be to bring the value of to bring the range as low as possible. However, that is limited by a term which is called the critical radius of connectivity, which has been shown as the lower bound is square root of log n by pi n, where n is the number of nodes. But we don't want to go into that because that's not part of this. We move on to the analysis. We shall be looking at the assumptions in this model, the model itself, the different types of transmissions, and finally the expected throughput. So I'm following the assumptions made by the authors in their paper, namely there are n nodes in a unit area circle. Over here, of course, Qn of them are access points, and 1 minus Q times n are the wireless nodes, and they are arbitrarily located on the plane. Each node is capable of transmitting at W bits per second. And finally, the wireless nodes have a common fixed transmission range. This is the physical model on which the analysis is based. Namely, at any given time, only a single receiver if xj is our receiver and xi is the transmitter, then xj receives the signals from xi, but every other transmission from the k other nodes, k minus 1 other nodes, are perceived as noise. And this signal divided by noise, the signal to interference ratio should be greater than beta. Based on this, the analysis is performed. And since we are looking at a heterogeneous system with 2 types of nodes, I've tried to divide the work into 4 kinds of transmissions, namely node to access point to node, and finally access point to access point. And these are the probabilities of it occurring, namely what is the probability that a node starts the transmission and it is received by a node, and so on. Now this might be a little simplistic, to say the least, as Dr. Yates has pointed out, for one reason that this is a kind of end-to-end transmission, and we are not looking into what's happening in between. And moreover, we are not considering the traffic patterns that might be involved in an actual transmission. So this is a little simple, and I hope to work on this further to make this more satisfying. So instead of going into the details of the derivation, I'm going to show you the final results that were obtained. And my paper is on the web, so you can take a look at it. I'll give you the website at the end. So for a node-to-node transmission, the transport capacity was this, and the throughput, which is by dividing by the number of nodes, namely in this case 1 minus Q times n, we get this result. And interestingly enough, this is nothing but a scale version of the results obtained by Gupta and Kumar. So over there it was, you would just not be having this factor, 1 minus q. Over here, since the number of transmitters are 1 minus q times n, the capacity and the throughput were obtained in that form. In the case of the node to access point transmission, since the number of wireless nodes which are transmitting are still the same, the result is again the same. And again, I would like to point out that this is because of the assumption that all the 4 types of transmissions are mutually exclusive. So if we consider traffic patterns and we consider the node and wireless access points, the wireless nodes and the access points in between, the result might be a little different. Finally, since the number of access points is Qn, in the case of access point to node transmission, the result is obtained as this. It's scaled by Q. And an access point to access point transmission, which is nothing but a wired transmission, gives this result.
In terms of Gupta and Kumar, right, you have a sort of a non-hierarchical structure, right? All nodes are the same.
That's right.
And throughput per node is defined as like there's a random set matching of nodes as pairs, right? And it's the between those pairs, it's the throughput you can expect, right? Averaged over the pairs is what you call throughput per node.
Averaged over the pairs for all nodes, yes.
Right. And then transport capacity is the sum of all those
Summed over all the nodes.
over all the pairs.
Yes.
Right.
Yes.
And okay, so in essence, it's like in the context of your physical system, I'm not sure exactly what these things mean.
Which
Like, so, and maybe it's clear to everybody else, but it isn't to me.
Looks like he has 4 separate systems.
Like how are these 4 different kinds of communications? So there's node to node, access point to access point, and then the 2 other combinations.
Right.
So for instance, like let's start with this one. Access point to access point,
Okay.
right? Like sort of what does this mean? It's the okay, I'll ask you a question, right? If there's a node who wants to really, all the real communication in the system is really from node to node.
Right.
In the sense that you have actual nodes that want to communicate to other nodes, just like Gupta and Kumar, right? And then sometimes that traffic, like they say, instead of following some node to node, the route, right? The route has a shortcut through an access point into the wired network to another access point and back out to this node, right?
Right.
Is it true that, like in your assumptions, that all traffic between nodes actually travels this way?
No, it assumes since the number of access points is Qn and the number of wireless nodes is 1 minus q times n, it assumes that, supposing it's, let's take the case that the transmitting node is a wireless node. So it assumes that the wireless node, the next hop neighbor of the wireless node is an access point with a probability q by, with a probability q divided by q plus 1 minus q. And that the next hop neighbor is another wireless node with a probability of 1 minus q. And then it's summed up.
So in essence, you're saying like the model for the route something follows is like it goes sort of it's a kind of a, you go one hop and you either, depending on whichever these two sort of density measures, you
Right.
get either to the access point or to some other node in a sort of with a memory list flip a coin kind of thing.
Right. Everything is
And
in-
then if it's to another node,
Right.
right, you flip another coin,
And decide again.
right, and maybe you get to an access point or not. Is it possible, like, that you get to your destination, or is it what it really means is you have some geometric number of hops till you get to an access point, and then some geometric number of hops out of some other access point
To the destination.
to the destination?
Yes.
So how do you model that? So okay, so I understand the idea. I'm not sure if it's a good model or a bad model, but it doesn't sound ridiculous to have this coin flip to get to the access point, right? But when you think about reaching some other node through some other access point, like what physically would happen is you would choose an access point that's like the closest to the person,
Right.
to that other node. And then the fact that it's the closest says that there's something unusually, like the number of hops to reach it should be pretty darn small.
Okay, but if you look at it from the power point of view, then it might require less energy to transmit, instead of in a single hop to the access point, through multiple number of hops.
I guess what's weird here is if whatever model you use to say, oh, like the first link from, I guess you guys can tell this is not a finished thing. So jump in, right? Like we're here to give them some advice and figure out what his feelings. Like whatever model you use from the first node to the access point, right? For it takes about this many hops. Right? Symmetry says it should be about the same thing from some other access point out to the final destination, right? Just because if you did the communication the other way, right, it would be.
So you are saying it's just like a reduction in the number of nodes in the system. Depending on what queue you use, for every one of these randomly chosen pair, you have a reduction in the number of hops, and therefore equivalently reduction in the number of nodes. So
Well, I think.
think of it that way, and just take Kuma's result and put in this reduction factor.
It's almost like the so the number of hops something travels, right, is 2 times the number of hops from a node to the closest access point. But on the other hand, right, so is this like a reasonable model for the number of hops to the nearest access point, or is this so for instance, do you do you know if this model is like reasonable or not yet? And I'm really serious.
It did give a better result than what you would get without access points.
No, what I mean is, like, if you actually spread the nodes out on space, right, and then say calculated, say you could calculate like some kind of a shortest path route to the closest access point.
Yes.
Like, does the number of hops to that averaged over all the ensemble of all placements and all nodes to all, all of that? Like, does it appear to have any kind of distribution, sort of like this geometric? Okay. So
relating to Roy's question, I think what people really want to know is this: choose 2 random wireless nodes in the system. What's the average throughput? So you classify these 4 types of transmissions, right? So do you mean that out of these 4 types of transmissions, you will calculate what I just asked? So suppose you pick 2 random,
Okay.
right, wireless node. On the average, what's the throughput between them? Is it your wireless node to wireless node, or you have to derive it from?
It will have to be derived
Okay.
because a wireless node to wireless node transmission would have these transmissions in between.
Okay. Fine.
So let's take the case in Q is 1, right?
Okay.
Everything's an access point,
Right.
and then your throughput per
constant.
access point to access point will be is it
It's a
actually
constant.
this tau
Yes.
W2 over root pi?
That's right.
So physically, what would that mean?
That means the wired channel between access points has a constant throughput, irrespective of how many access points there are in the system.
So it seems to me, right? Like if you said everything is an access point, which means everything travels through the wired network, and there's no radio contention, there's no nothing, right? Then your throughput per node should just be the offered load per, like somehow. Am I making any sense? It's whatever it is you define as sort of the input traffic load, right? Averaged over all the pairs.
So until you hit the bandwidth. Oh, but this is the wireless bandwidth. Okay, I mean, I got confused. I thought somehow this is the bandwidth in the lines.
Now the throughput of the nodes is given by lambda, and this is the upper bound. So what you're saying is right, that it depends on the load that's being offered in lambda, how many transmissions are being made. But if it transmits at its full capacity, then it cannot exceed this limit. And if you can take a look at the paper later, that's how it was derived. That the throughput per node.
So why should the wireless bandwidth factor into this? W is
Is the
bandwidth.
capacity of the yeah.
I guess some of the question is like, do you think of your access points as participating in the wireless network?
They have to.
Huh?
They have to transmit from the access point to the final destination. If that is a wireless node, then it has to participate.
Yeah, but maybe the way to do the bookkeeping, right, is to like only count the node to node throughput, right? And the fact that a lot of it is going through access points, like they shouldn't be part of your end. They should be sort of an infrastructure. Does that make any sense? Like you could make an argument that says, oh, like I have, like you could sprinkle the surface with access points in some density relative to the density of nodes, right? But then you just count node to node throughput, and the result is if there are no wireless nodes, there is no throughput, just because there's nothing there.
Okay.
Right?
Okay.
Maybe.
Look into that.
Because like this is very confusing, right? Because like maybe there shouldn't be a bound when it's all access points if the wired network part is completely free. So can we go? Do you have more slides?
Yes, I have the plots.
Oh, you have plots? All right, let's get some plots.
I had assumed that the access points also participate in the traffic, and they might also generate information on their own.
Yeah.
So we look into just wireless to wireless transmission. And this is the expected throughput per node obtained from the probabilities earlier.
So when traffic originates at an access point, do you still have, like in the analysis, this geometric number of hops to an access point?
No.
So somehow that is then discounted?
It is there when the final destination is a wireless node.
But only
at
on
the
one
end.
side,
Yes.
the other end, okay.
So let's move on to the results and take a look at the plots that were obtained. I tried to do it in terms of the expected throughput versus the fraction Q of access points, and also by keeping the number of access points constant and increasing the number of nodes, or rather keeping the fraction constant and increasing the number of nodes. So here is in an area of 1 meter square, 100 nodes with a system throughput of just 1 kilobits per second, which is quite low. The signal to interference ratio was chosen as 10 decibels, and we find that as the fraction of access points is increased, the expected throughput increases.
So how did you get a figure like this?
By plotting this
Oh,
throughput.
so you're just plotting your functions.
Yes.
Okay.
And by changing the number of nodes or by changing the W, it merely rescales the figure. This is the more interesting result when we choose different values of Q and see how the behavior changes with the number of nodes. This is the result that was obtained by Gupta and Kumar. My results also agree with theirs when Q is equal to 0, and we find that the throughput decreases with the increase of the number of nodes. The number of nodes is varied from 1 to 1000. Now, when the Q is changed to 0.1, that is, there are 10% of access points, the behavior of the curve is pretty much the same, but the lower minimum is now not going to 0, but slightly higher. And we find that as Q is increased, this gradually goes higher. And that follows from the fact that the fourth part of the result that I had, namely from access point to access point transmission, that was a constant. So it's merely adding to the earlier graph. This is a 50% fraction of nodes at access points.
Was there a difference in the plots?
In what's
Like
that?
if you, like somehow you click the key and Q change. Can you go back one?
I'm sorry.
But what's the difference in the two?
The scale over here starts from 0 on the y-axis, and over here it starts from 300.
Oh man, you killed me with this stuff. So what's wrong with like just putting a few of them all on one plot for different values of Q,
Okay.
so we could figure out what the deal is?
Okay.
And also, don't ever do this start at 300 business. You know, it's classic New York Times. Do you know what I'm saying? Like you just, you know,
Misleading.
yeah, right.
This problem point for 0.9, it starts from 900.
So what does it mean to have like a small, like what are these, you know, like so do the results for small numbers of nodes mean anything?
When the number of nodes is small, that means the density is very low. So the interference will be much less. So whether there are access points or not, the results are not much affected because there isn't too much interference anyway.
Q equals 1.
You guys agree? I don't know, because like then you, I guess you should get to some limit, right, where you get a lot of direction. Like are these these are not throughputs per node, right?
Yes,
Or they are?
throughput per node.
Okay. As opposed to the other throughput thing, what did you call the other one?
The capacity, the transfer
Yeah.
capacity. If I were to plot that, then it would be an exponential increasing curve. And for all access points, it's constant. So we notice that there is an improvement for a higher number of nodes. Mainly the capacity doesn't go down as much as it would without access points. Thus, there is a minimum quality of service that's assured by the wired access points. And as was pointed out, the results do agree with Gupta-Kumar's results when the fraction is 0. So this was the original paper by Gupta and Kumar on which this analysis was based. And my results in the form of a paper is available on my website, and this is the URL.